All right, welcome to this explainer. Today, we're diving into something completely invisible, yet literally surrounding us right now. I mean, we interact with magnets all the time, right? They stick notes to our fridges, power all our electronics, and tell us where we're going. But what is this invisible force really? And how does it connect a tiny subatomic particle to the churning core of our planet? Think about it. Where exactly is north? Sounds like a super simple question, right? Well, actually, the answer is going to take us on this wild, scale-jumping journey from the center of the Earth all the way out to the edge of space. What we think of as its basic, fixed direction is actually a constantly shifting consequence of intense planetary physics.
So, here is our roadmap for the day. We'll be looking at Earth as a giant magnet, the physics of magnetic fields, our cosmic solar shield, making sense of north, and finally, navigating a changing field. Let's get to it.
Section 1. Earth as a giant magnet, also known as the planetary dynamo.
Way down deep inside our planet, there's a massive engine. Picture this. You've got liquid, molten materials, mostly iron and nickel, churning around in the outer core. Combine that crazy liquid convection with the Earth's daily rotation, and boom, you get electric currents. This interaction creates a massive dynamo effect. It is basically as if the Earth had a gigantic bar magnet jammed straight through its center.
Moving on to Section 2, the physics of magnetic fields, where we are zooming all the way into the subatomic level.
It's actually wild to look back at how we figured all this out. We started in antiquity with ancient Greeks playing with magnetic lodestones from magnesia. Fast forward to the year 1600, William Gilbert realizes the Earth itself is a magnet. Then, in 1820, Hans Christian Ørsted proves that electric currents actually produce magnetic fields. By 1860, Maxwell drops his famous equations unifying electricity and magnetism, and finally, in 1905, Einstein steps in with special relativity to tie the whole electromagnetism package together across all reference frames. What a historical ride, right? Now, at this super tiny scale, it all comes down to the Lorentz force, the force exerted on a moving charge. And there's a really weird quirk here. The Lorentz force is always perfectly perpendicular to the charge's velocity. Always. Because of that 90-degree angle, it actually does zero work on the particle. That means a magnetic field can only ever change a particle's direction. It can literally never speed it up or slow it down. Mind-bending, isn't it? So what happens to that moving particle? Well, if it hits a magnetic field head-on at a perfect perpendicular angle, it gets trapped in a flat, circular orbit. We call that spinning the cyclotron frequency. But in the real world, it usually hits at an angle, so it has both parallel and perpendicular components. Because of that, instead of a flat circle, the particle spirals forward. It traces out this beautiful three-dimensional corkscrew, or helical path. Keep that spiral in the back of your mind, because it's about to be a huge deal. All right, Section 3, our cosmic solar shield. We're zooming way back out to space for this one. So that planetary dynamo we talked about earlier, it projects our magnetic field thousands of miles out into space, creating what we call the magnetosphere. Think of it as our planet's ultimate invisible force field. It blocks highly dangerous, high-energy particles zooming at us via solar winds. I mean, without the magnetosphere, severe solar storms would just absolutely fry the planet. Life as we know it would be completely impossible. Okay, remember that tiny corkscrew motion we just talked about? Well, when charged particles from the sun, like protons, slam into our magnetic field, they get caught in these zones called the Van Allen belts. And they don't just sit there. They trace those exact same helical paths, spiraling wildly back and forth between the north and south poles along the field lines. When those spiraling particles finally crash into our upper atmosphere, the resulting energy release creates the breathtaking northern and southern lights. So yeah, the auroras are basically just giant glowing atomic corkscrews. Which brings us to Section 4, making sense of north. Let's land this physics lesson right back in your hands.
If you're out in the wilderness holding a map, you really need to know the difference between true north and magnetic north. True north is geographical. It's the direction of a longitude line pointing straight to the physical top of the globe. But Earth's magnetic field is, well, it's a bit messy. It is not perfectly symmetrical. So magnetic north, the actual physical spot where the magnetic field lines plunge straight down into the Earth, is in a completely different location than the geographic pole.
This is exactly why top-tier topographic maps, like the ones from the U.S. Geological Survey, brilliantly solve this headache by giving you 3 different north arrows. You've got a star for true north, MN for magnetic north, and then GN for grid north. Grid north is just a handy mathematical fix for trying to flatten our round planet onto a flat two-dimensional piece of paper, using systems like the Universal Transverse Mercator. The angles between these three arrows tell you exactly how much you need to mathematically adjust your compass to actually get where you're trying to go.
And speaking of your compass, why does that little physical needle always naturally swing to follow magnetic north? One word: torque. That tiny needle is a magnetic dipole. Just like a loop of wire carrying a current feels a twisting force when it's placed inside a magnetic field, your compass needle feels that exact same torque. It's an invisible force physically pushing the needle until its own magnetic moment perfectly aligns with Earth's surrounding magnetic field.
And finally, Section 5, Navigating a Changing Field. Let's look at the future of our magnetic shield. Here's where the story gets incredibly dramatic. Our magnetic field isn't this permanent, locked-in grid. It is highly unstable, and it's shifting right beneath our feet as we speak. Because that molten iron core is a swirling fluid, the magnetic poles actually wander around over time. For instance, back in 2001, magnetic north was hanging out near Ellesmere Island in northern Canada. But recently, it's been practically sprinting east, leaving the Canadian Arctic entirely and making a total beeline straight towards Siberia.
And get this, it's not just moving, it's actually fading. During the early 21st century, the overall strength of our planetary magnetic shield decreased by an average of 1.7%. And in a few specific regions, it has dropped by a whopping 10%. That is a massive shift. Now, a weakening, wandering field isn't just annoying for hikers trying to read a map. It is a huge deal for global ecology. Think about migratory animals. They are literally born with an internal magnetic map. They sense the intensity of the field to navigate thousands of miles safely. They rely on it to establish their circadian rhythms. Some species even have actual magnetic particles built right into their biology. Their entire existence completely depends on this invisible force remaining stable.
So what happens if the field strength keeps dropping? Well, Earth's geologic history tells us exactly what happens. When the field strength drops all the way to zero, the whole thing eventually boots back up. But in reverse, it's called a geomagnetic reversal. The North and South poles literally trade places. It is a massive, epic planetary event that can take thousands of years to fully complete.
Which leaves us with one massive, looming question at the end of all this. We know for a fact the poles have flipped before. And we know the field is demonstrably weakening right now. So what on earth is going to happen to our modern, hyper-connected, technology-dependent humanity, and to those millions of migratory animals when the poles inevitably reverse again? It's a profound, invisible mystery, hiding in plain sight, right at the tip of your compass needle.